Hey, Mr. Bells here again. We're going to talk a little bit about specific quadrilaterals, kites, and some trapezoids right now. So here we go. Hopefully this is all good for you. So, we've been talking about quadrilaterals a lot in these units, or else you probably wouldn't be watching this video right now. So one of the quadrilaterals that we're going to talk about, again, quads being any polygon with 4 sides, is something called a trapezoid. And a trapezoid basically has this situation going on in that it has at least one set of parallel sides. And when you have one set of parallel sides, that means that this angle right here, x, and this angle right here, y, that x plus y, the two angles that are interior, must add up to 180 degrees. And that over here, z and w, that z plus w must also add up to 180 degrees. And that's kind of the rule for trapezoids in terms of some of the basic properties. Now, one of the things that we would know is if a shape's a trapezoid if we had talked about slopes. So if this was in a coordinate plane, you would have to have at least 2 of the sides of it whose slopes are equal. We would know that that would make it a trapezoid then. Okay? So what are some of the other special situations with these? Well, in this case, just to make sure that we are okay with this, if I put a single mark on that, I don't have to have a single mark there. It doesn't mean that the upper side and the bottom side are congruent. They're definitely not. They're different lengths. Just like here, this could be 3 tick marks and this could be 4 tick marks. None of the sides have to be the same. Now they could be the same, but they don't have to be the same. The only thing that you have going on, again, is at least one of the sides parallel to another one of the sides. Now, that again is called a trapezoid. However, we have special types of trapezoids. There's another one called an isosceles trapezoid, and it has a few more properties than just a regular trapezoid. An isosceles trapezoid looks like this, where you still have, just like a regular trapezoid, you have a pair of parallel sides just like that. But on an isosceles trapezoid, you also have the two non-parallel sides. Two non-parallel sides are congruent. Just like if you had a isosceles triangle and you split it all the way up there, it's just like truncating it or cutting off that isosceles trapezoid. Now, if that's the case, now just like before, x and y add up to x plus y, add up to 180 degrees. Again, remember, we're talking about angles. That means the opening, the measurement opening between those two rays. However, on an isosceles triangle, this is also x and this is also y. So that means that these two base angles are congruent and these two angles up here are also congruent. Which means you could also do some stuff with some symmetry and some other things. So like for instance, if for example we had some measurements out here, I'm just going to do a little bit of one right here, and we had this like this, and these two things were congruent and these two things were parallel, and this up here was 16 and this down here was 20, then we would be able to go, oh, well, if I drop this straight down and I drop this straight down, then this distance right here must also be 16, correct? And if the whole thing's 20, then that must be 2 left over there and 2 left over there. Now, if we were also to know this, say this was an 8 right there, yes, then since this is a right triangle, I know that I would have, I'm just going to blow this triangle right here, and let's call this A, B, and that little part C, A, B, and C. I would have a right triangle right now with a 2 here and an 8 here, which means I could use Pythagorean theorem, Pythag, to be able to find out this side over here. I could also find out this angle B. I could find out what that angle B is, which is, of course, would also be this angle D way over here on this side because of the fact that those two angles have to be the same. And I could do that by using, right, this is my person. I'm going to go through this whole thing again from right triangle trig stuff. And if you haven't seen the right triangle trig stuff, you'll see it later. But I think maybe most of you have seen this now. That this side would be the opposite and this side would be the adjacent. And we know we have so, ka, toa. And opposite and adjacent would be a tangent. So then I could write the tangent of that angle B is equal to the opposite side 8 over the adjacent 2. And then I would hit tan inverse on my calculator, and I would do it on the other side too. So on my handy dandy calculator right here, I would check my mode first, make sure I was in degree mode, right? We know that on our home screens, if we hit tan 45, degree mode's always going to give us a 1, so that's good. If it doesn't give us a 1, make sure, you should check it on your calculator right now, make sure tan 45 gives you a 1. If it doesn't, then you do have to change your mode to degrees because it's currently in radians. Okay? So I go back to my home screen here, and it says I'm supposed to do the tan inverse of 8 over 2. So second, I get my tan inverse, the little -1 thing right there, of 8 divided by 2, making sure that's all together in the parentheses. And I hit enter, and that would mean that that's a 75.96 degree angle. So that angle right there is 75.96 degrees. Now, since this angle here and this angle up here, A, right, angle B is equal to 75.96. Angle A has to be supplementary to it, right, because those two angles have to add up to 180. So I simply could go here, 180 minus my last answer. I know that angle A is 104.04 degrees, if I rounded. Okay? So just some of the things that you can do with it. And of course, you could find perimeters, you could find areas, you could do any of those things with it. Know that you know what's going on with that type of isosceles trapezoid. Okay? So the next shape that we're going to talk about after an isosceles trapezoid is something called a kite. And a kite is basically a quadrilateral, and it's going to have some specific properties to it. You know, if you've already done this, right, that if all 4 of the sides were equal, that would be called a rhombus. On a kite, it has two sets of adjacent sides that are congruent, just like that. And when you have a situation like this, then this happens to be true. It happens to be that this right here, this red line, or the diagonal from the vertices between the differing sides, and the diagonal here between the vertices on the congruent sides, this will always be perpendicular. That's kind of a cool fact for kites. And again, anytime you get right angles in there, then you have that whole isosceles or whole right triangle trigonometry stuff that you can use to do lots of different math with it. That's why we covered all that right triangle trig beforehand. Okay, but what are some other things about this? One, this happens to split the sides between the segment that goes between the differing side lengths. It splits them into two congruent parts, so it's a perpendicular bisector there. So this diagonal that goes through here is perpendicular bisector. Now, this angle right here and this angle right here, I'm going to use a dot and a square. These two things are not congruent. So this is not an angle bisector right there. However, these two right up here and these two right down here, even though they don't have to be the same size as the ones up and above, or above and below, they are congruent to each other. So this angle and this angle is congruent, this angle and this angle is congruent, this 2, 3, this angle and this angle are congruent, and last one, I'll just put a square in here because I got so many different lines in this little red box. Those two angles are congruent. So a kite has lots of properties that you can pull off, and again, we can talk about things like if this was in a coordinate plane, if you had vertice A, B, C, and D in a coordinate plane, and you could prove that AC by the distance formula is congruent to AB, and you could prove that CD is congruent to BD by the distance formula, then you'd know this would have to be a kite. And if you know that that's a kite, then you'd know that the slopes of that AD would be perpendicular to BC, right? You'd know that if this was, let's call this point E right in here, point E, you know that CE is congruent to EB because those have to be perpendicular bisectors. Then there's all kinds of different stuff that you can get following the information from these kites. Again, this is supposed to be just a quick video review of what trapezoids, isosceles trapezoids, and kites are, and then your goal is to be able to put together all the math that we need to through Pythagorean theorem, through trigonometry or right triangle trig, SOHCAHTOAs or SOHCAHTOA inverses, any of those things that would be able to help us find that. So I'm going to give you a couple of quick examples right here again, just as a reminder for your Pythag stuff. Say you had a right triangle that looked like this, and this length happened to be 12 here, and this length right here happened to be, let's call that 7, and I wanted to find out how far it was from A to B. Well, we'd call that x as our unknown, so we would write x squared plus 7 squared equals 12 squared. And then you do x squared plus 49 equals 144. And then you'd write x squared equals, and subtract the 49, right, from the other side. And then it's kind of like subtracting 50, so 50 away from that would be 94, so it's going to be 95. Now, I don't know what the square root of 95 is, and I could do my little simplified radical form, or I could just get an approximation. And for right now, I'm just going to go ahead and do an approximation. So the square root of 95, and again, since the square root's 100, is 10. This is going to be a little bit less than 10. So I'm going to do square root of 100, and see, 10. So if I do square root of 95, I get 9.75, or something I thought was going to be really close to 10, and it was. Okay? That would be an example of Pythagorean theorem, and again, if I had these, because I have 4 different right triangles in here, I could use that as part of my mathematical properties with this. The other thing I could do is if I had, for instance, this situation, and I had a right triangle here, and maybe this was part of, right, maybe this was part of a kite, and I was given some information for it, maybe like this was 23 degrees, and that this right here was 5, and I wanted to know how far it was along the outside portion of this kite. Well, I can do that. In fact, there's a lot of math that I can do right now with this. So I do know if that's 23 degrees, then that's also 23 degrees, right? And if that's 5, then this road over here would have been 5 because they have to be part of the situation with my kite. But I'm going to find my x. So I'll put my person right here. And this side would be considered the opposite. And the side I'm trying to figure out is considered the hypotenuse. So I want O and H, and O and H is sine. So I would write sine of 23 degrees equals my opposite 5 over my hypotenuse x. And I'm trying to solve that equation. And if you remember before, we said whenever the variable is downstairs, you can simply just switch its spot with the trig ratio right over here. So then x is equal to 5 divided by the sine of 23 degrees. And I go ahead and pull this out. So 5 divided by sine of 23. And I get 12.79. So that would be my x, 12.79. So as I've talked about these trapezoids and isosceles trapezoids and kites now, you can see where all of the math comes back into play between Pythagorean theorem, regular sine, cosine, tangent, and then sine inverse, cosine inverse, tangent inverse. Now, let's say I screwed this up and I did this the other way, and I did 5 times the sine of 23, 5 times the sine of 23. I'd get 1.95. Well, at least in that case, I could write that in there and then go, wait, what? That doesn't make any sense. So please check, just like I've preached since the first day in my classes, check to make sure that your numbers make sense. Probably a majority of the time, sorry about that. A majority of the time, if it doesn't make any sense, then you probably did it wrong. And if you did do it wrong and it still does make sense, hopefully you'll catch it sooner rather than later. Okay, that's Mr. Bells. We'll talk to you later.